Hello everyone. Now these three categories, you see lots of methods proposed in last 2-3 years. We discussed knowledge editor from global optimization category. We discussed Rome from this category. All right. Now let's move into the next method for knowledge editing, and this is called grace. We update knowledge with grace, and this is essentially a technique which belongs to this category of external memory, right? You basically include you insert external memory to the model, and this external memory will be responsible for capturing the edits, capturing the new knowledge. This is comparatively easier than the previous one. Okay, but let's first understand the heuristics or hypothesis, intuition behind grace. The idea is as follows. What we do here, we will add an external memory which they call grace adapter. Now this is not the adapter that we already learned, right? This is not that kind of adapter. This is not a parameter efficient fine tuning method. This is an adapter. They call it adapter. Adapter is just a cache memory, an external memory. You can think of it as a database, right? Or some sort of code base. Okay. So this adapter is responsible for storing the edits, so storing the new knowledge. Okay. Now, when a knowledge is stored into the adapter, right, or when a knowledge is stored into the memory of LLM, they said that along with the knowledge also has a periphery of its spread, right? Let's say if you think of a knowledge, a specific knowledge, right? Let's say you represent the knowledge by a key value pair. Okay. Now this key value pair that I'm talking about here, this is not the key value that we discussed in attention. Okay. This is a different terminology of key value, which we'll discuss maybe in the next lecture, right? Which essentially says that this multilayer perceptron MLP is a knowledge storer, right? There, so you know that in MLP there are two layers, right? One layer is essentially kind of a fan out, right? It up projects things, and the other layer down projects things, right? Fan in. So when we do fan out, right, the resultant embedding will act as a key. It's a complicated concept. We'll discuss when you talk about interpretability, right? But the idea is that, I mean, for the time being, you assume that every key or every knowledge is essentially represented by a key value pair. Okay. Now, when we store a key, now key is just a representation, again, an embedding, right? When you store a key, so in a vector space, this is one vector, right? And the vector as a span. Let's say this is the vector space and this is the key. The key has a span, and the span essentially intuitively captures different paraphrased version of the key, right? And so every knowledge has this center, right, and some sort of periphery, and this periphery is captured using a radius r. Here the radius is epsilon. Okay, so when a new knowledge comes in, it comes with a key and a radius, and all the knowledge which are already stored into the memory, they also have keys and radius, right? This is the concept, and we will see how we update this. Okay, so they came up with the concept of grace adapter. Grace adapter consists of two components. One is the simple code base or a knowledge base, okay, C, and the other is called a deferral mechanism. Again, we'll discuss what is deferral mechanism. A code base and a deferral mechanism. Please pay attention to this, okay? Please don't get lost. So, as I mentioned, let's say this is my code base. Let's say this is my code base, okay? Here all the knowledge are stored. Every knowledge has a key and a value and a radius. Okay, small k, small v, and radius epsilon. Okay, and we learn this epsilon, learn key, we learn v, we learn epsilon, right? But let's say this is my memory. In this memory there are 4 concepts which are stored, 4 knowledge which are stored, right? And this small circles indicate the actual knowledge embedding, and the peripheral circle indicates their span. Okay, all right. Now let's look at the algorithm. I will discuss the algorithm as well as the pictorial representation of the algorithm. So code base is just a memory which looks like a code base, right, where you store the key, the value, and the radius, k, v, and epsilon for every concept, for every knowledge. So this grace adapter is basically attached to a layer. Think of this transformer, right? We have layers, right? Layers. So you basically add this grace adapter to one of these layers. Now which layer? It's not clear, right? So in the next algorithm which we'll discuss, ROM, we'll see that ROM identifies a layer which is responsible for this editing. Now you can actually combine ROM and grace together with ROM identifying the location, and then you add this adapter. For the time being, we assume that you will add this adapter to the lth layer. Okay, so this is the code base memory that we want to add adapter. This is my model F. Okay, what is x sub t? X sub t is the desired output, Joe Biden, right? What is xt? Xt is the input, the president of the US, right? Now xt is such an input for which the output is not yt, right? The output is Barack Obama, but you want it to be updated to Joe Biden, right? What is this epsilon init? Epsilon init is the initialization of the epsilon for every knowledge. As I mentioned, with every knowledge we have this epsilon radius, right? So we initialize this with epsilon init. Okay, for this algorithm we need a distance function. Distance function can be cosine, can be Euclidean. Let's assume that the distance function is d. Okay, the algorithm starts. Look at this line. So now this is the lth layer which I am interested in, and I would like to add an adapter here, and this is my L minus 1th layer. This is L minus 1th layer. Okay, so if L minus 1 xt is what? So xt is the input to the model, right, to the model, and this is the output of L minus 1th layer, right, and we denote this by h L minus 1. So the output that I obtained from this L minus 1 layer is h L minus 1. Clear? Clear? What is h capital L xt? Capital L is the number of layers. So capital L is the last layer, right? So the last layer's output is y hat. So what is y hat for the query the US president is? Barack Obama. Y hat is Barack Obama. This is the outdated knowledge that I want to update, right? All right. Now this h L minus 1, this h L minus 1 is the key, for my knowledge. Okay. Now I already have this code base C, the adapter C, where all the knowledge have already been stored, right? Now this is denoted by k1, k2, k3 dot. These are knowledges which have already been stored, right? Assume that this algorithm has been executed multiple times, and you already added some knowledge into the code base. Now when this new knowledge comes in, which is h L minus 1, right, what I will do, I will check whether this knowledge already exists into the code base or not. It may happen that it already exists, right? How do you check this? Now remember, all this knowledge, right, they have a So all this knowledge are basically circles, right? They have their radius, so knowledge ki and their radius epsilon I, right? Now this is a new knowledge. This is again represented by a circle, right? And what is the radius for this? What is the radius for this new knowledge? The radius is epsilon init. Okay, so what I will do now, I will check the similarity between the new knowledge and all the existing knowledge present in the code base. Okay, to check whether they exist or not, this particular knowledge exists or not. And how do you do that? We measure the distance between HL minus 1 to each of these k's. So distance between HL minus 1 and each of these k's, ki, right? And which one I'll pick the minimum one, because the minimum distance knowledge essentially indicates that this is the most similar knowledge which is present in the code base, right? Let's say this is ki. Clear? So far so good. So ki is the most similar knowledge which is present in the code base with respect to HL minus 1. Now, how do you know whether these two knowledges should be merged or what? Now depending on the situation, there can be multiple if-else condition. The first if condition says, look at this if condition. Now what is the d mean? D mean is the minimum distance, is the distance between essentially these two, ki and HL minus 1, right? This is d mean. So the minimum distance between the new knowledge and the existing knowledge present. So if d mean, so basically let's say this is the new knowledge and this is the existing knowledge which is similar, and this is d mean, the distance between these two, and this circle has a radius epsilon init, and this has a radius of epsilon I, ith knowledge epsilon I. So if the distance between two centers is greater than epsilon I plus epsilon init, what does it mean? They are not overlapping. They are not overlapping, right? It means that this new knowledge HL minus 1 is a new knowledge that you need to store separately. It's a new knowledge. Clear? It's a new knowledge because this HL minus 1 doesn't come under the span of xi, right? So this needs to be stored separately. So now I knew that the key is HL minus 1. So key value pair, right? The key is HL minus 1. But what is the value corresponding to this key? I know so I already mentioned that in a code base, every knowledge is stored using a triplet, k, v and epsilon. I know the k, which is HL minus 1. I know the epsilon, which is epsilon init. What is v? We don't know what is v. We need to learn v, right? And how do you learn this? So when a new knowledge comes in, the value is initialized with a random vector v init. When this new knowledge comes in, so for HL minus 1, there's a v init. Okay? And I pass this v init to the next layer of the transformer, which is L plus 1. I pass this to L plus 1, and this will be propagated till the end, and the loss will be computed, right? How do you compute the loss? What is the ground truth? The ground truth, I already know the ground truth is Joe Biden, right? So if the model returns Barack Obama instead of Joe Biden, there will be a loss, and the loss will be back propagated, and the entire loss will be differentiated not only with respect to the parameters of the model W, but also this v init. Okay, so v init will also act as a parameter. This will also be updated. Clear? And this is written here. Look at this line. So p of ppf y given v init means what? Y is the output, right? V init is the input from that layer, condition on this and I fine tune the model, and that fine tuning will, periodic fine tuning will basically return V new, which is the value for the new knowledge. And the paper, they said that for every new knowledge they fine tuned the model 100 times, 100 or 20 times, I don't remember exactly, but they basically fine tuned it multiple times. Clear? So that is going to give me V new. And so I have this new knowledge which is HL minus 1. So this will act as a key. What is the value? Value is the V new. And what is the radius? Radius is the epsilon init. This will be stored to the code base separately. It's a database, it will be stored, appended. Okay. Now this condition will be executed when the distance between two centers is greater than the sum of the radius. This will also be executed when the code base is empty. If the code base is empty, there is no knowledge. So in this way, new knowledge will be added to the code base. Now look at the second condition. If this doesn't satisfy, then the second condition is what? The second condition can be, look at this one, right? Focus only this one. So the second condition says that the output of the model for this new key is Joe Biden. That means you don't need to change anything, right? So essentially what is happening is that this new knowledge comes in, which is the key is HL minus 1, and the minimum the concept or the knowledge which is similar to this is KI, right? And the output is essentially the desired output. What does it mean? What I need to change now? So this concept and this concept is the same. So it means I need to expand the periphery of the existing knowledge, because I need to also encompass this one, right? That means I need to increase the periphery of this knowledge, right? So how do you do that? You basically update the radius of the existing knowledge. Earlier it is epsilon I, now this is epsilon I plus epsilon init. So if you do that, the new knowledge which has come will be added, will be included to the new circle. What is the third condition? The third condition is the output is not Joe Biden, right? The output is different. So this is the condition. They are intersecting because this condition is violated. If this condition is violated, means what? The distance between two centers is lesser than the summation of these two. That means they intersected, right? If they intersected but their outputs are not the same, what does it mean? It means you need to separate them out, right? You need to separate them out. How do you separate them? You need to reduce the radius of the existing knowledge. The radius of the existing knowledge is epsilon I, right? What they did, they said that the updated radius will be d mean. What is d mean? D mean is the distance between two centers, d mean by 2. Very simple, right? So the updated radius for the existing knowledge, which is Ki, is d mean by 2. This is the updated radius. But remember this, these two concepts are different because their outputs are different. That means the new knowledge also needs to be stored. You separated them out by reducing the radius, right? You also need to add this new knowledge into the memory, right? How do you do that? The same concept. The key is HL minus 1. The value you need to learn is P init to V new, right? And the radius is d mean by 2, which you already identified. And how do you learn this? The same way. You calculate the loss, you backpropagate the loss, and you basically assume these as the parameters of the model, and you take the gradient of them. Okay, so the new entry will be added, the existing entry will be updated, right? Only the radius will be updated. That's all. This is it. So this is Grace. So Grace maintains a code base and the deferral. So these if-else conditions are called deferral mechanisms. Okay. So they tested their method, right, on two different data sets. This is a zero-shot relation extraction data, and this is a legal data, right? So this is their method Grace, right? And they tested is on T5 and bought 110 million size bot with full fine tuning, right? They also compared their method with Rome. They tested their method with respect to these two evaluation measures. You see here, Grace beats all the existing methods, including Rome, in terms of TRR, which is the which is basically success rate, and ERR is the retention rate of old edits. They call this method lifelong editing. Lifelong editing means this new knowledge which need to be updated are coming in streaming fashion, and you keep on editing this models again and again, right? So what happens is that after certain edits, it may be possible that some of the old edits will be lost, right? You keep on editing. It's a lifelong editing. You keep on editing whenever new knowledge comes in. Some of the old edits can be lost, right? So this ERR checks what is the accuracy of the model in terms of retaining some of the old edits. Okay. Now this is their accuracy and the average. This is the average of both TRR and ERR. Okay. So this is the end of Grace. In a nutshell, what Grace does, Grace essentially adds a Grace adapter, which is just an external code base, right? External knowledge base. And when a new knowledge comes in, it basically checks whether that knowledge is present in the external code base or not. If it is present in the external code base, the corresponding value will be returned. The value is assumed to be the updated value. That value will be returned, and that value will be passed to the next layer, right? If it is not present here, right? If the new knowledge is not present in the code base, right, it will essentially be added to the code base, and the corresponding V new will be learned, and V new will be passed to the next layer. In this way, the pretend knowledge will not be tampered. The pretend knowledge will remain the same. Additional knowledge will be added, and of course the criticism would be that number one, you are adding more parameters, right? But they said that, you know, the billion size of parameters, you are able to handle billion size of parameters. Why are you afraid of handling only a few parameters present in the adapter, right? The second criticism is which layer is selected for these edits. They said that you can add Grace adapters to all the layers, right? Or you can pinpoint certain layer, your favorite layer, maybe the middle layer or the last layer, and you add this Grace adapters. Okay, that's it. This is the survey paper that I strongly suggest you guys to read. This is a survey paper on knowledge editing. Many methods are presented here in a very nice way. I read this survey paper, and I also want you guys to read this survey paper. So after this lecture, I request you to read these three papers, and hopefully things will be clear. Okay, thank you.